okay. I checked my answer on that. It said negative x-axis, which would be that way to the right. So that was okay. So next I'm going to do is example 1010. A couple of people had questions about that. What is the power developed by a motor that turns at 350 RPMs when the torque is 3.6 Newton meters? Okay, and so for this, the power formula for motor is P equals 0.0105, all right, times the torque times the speed. So they get 0.105 times 300, well, no, the torque was next. The torque is 3.6. And 350 RPM. Now this formula is if your torque's in Newton meters and your speed's in RPM. If you have like your torque's in foot-pounds or something like that, they'll change whatever this first number is. But the power of a motor depends on how much twist it produces and how fast it is turning. Okay. Sometimes you hear people talk about motors. Oh, it's not power, it's torque. No, it's power. Okay. You can have torque and get no power at all. For example, if you are pulling on a wrench trying to loosen a bolt and you can't make it move, you can be hauling away on that thing with all your might and you're getting no action whatsoever. You have to have action to have power, okay, to make something move. So if your engine doesn't turn, nothing's happening. Okay, so I'll do the math, the book's math on this. 0.105 times 3.6 times 350. And they get 132 watts. Okay, so I get the same answer the book does. Now the related problem says determine the power produced if the torque is 5 Newton meters and the speed is 1,000 RPMs. So then my power would be equal to 0.015 times 5 Newton meters times 1,000. All right. So run that to my calculator. 0.105 times 5 times 1,000. 525 watts. Which is a little shy of a horsepower. A horsepower is 746 watts, 748 watts. Google it. 746. Roughly, ballpark figure 750. So that is example 1010. That's the power in a motor. Then the last one that people had questions about was 10.8. It said apply Faraday's law to find the induced voltage across a coil with 500 turns that is located in a magnetic field that's changing at a rate of 8,000 microwevers per second. That's pretty straight up. It's just your number of turns, okay, and then your rate of change. So it was 5 times 8,000, 500 times 8,000, 5 times 8 is 4, and then the zeros work out for your units induced 4 volts. The related problem says find the induced voltage across a 250 turn coil in a magnetic field that is changing at 50 microwevers per second, right? So your induced voltage is your number of turns times your change, which is this symbol. That comes from calculus. Whoever wrote the book, they want to throw some calculus symbols at you, just, I guess, to introduce you to it. So you have 250 turns times 50 microwevers per second. Okay, so 25 times 5 is 125, and then 2 zeros. So that's going to be in microvolts because this was turns in microwevers per second. So move over 1, 2, 3, 4, 5, so 0.01250 volts. 1, 2, 3, 4, 5, 6. Yeah. So check my answer on this. They're saying 12.5 millivolts. Yeah, I think that looks about right. That's microvolts. 1, 2, 3 over. Yes, that would be 12.5 millivolts. So that makes sense. All right. Well, I hope I answered your questions. And I know if I didn't answer all your questions, I at least showed you some cool stuff.